Fred is going on an airplane to visit another college. This time he remembers to close his shampoo not so tightly and put it in a Ziploc. He's also bringing with him on the airplane a bag of chips. When he gets to high altitude, the bag of chips is swollen and puffy. So what happened? Well, we know that the pressure changed. At a higher altitude, the pressure is lower. The pressure went down in the air outside of the bag. And as a result, something happened to the volume of the air inside the bag. The volume went up. We might also want to look at the number of moles of air molecules in the bag. Well, if the bag is sealed, that number will be the same. And the temperature of the air molecules. We'll assume that the cabin temperature has not changed. You may guess from the variables that I've given you what relationship we're going to look at, something you have seen in chemistry before. The ideal gas law is used to show the relationship between pressure, volume, and temperature of an ideal gas. The equation is PV equals nRT. P stands for the pressure of the ideal gas. Well, we talked about the bag of chips, but in most physics questions, it won't be just any gas. It'll be an ideal gas. The volume of the gas, the number of moles of the gas, the constant R, which this is one way of writing it. If I use this value, 8.31 joules per mole Kelvin, then my temperature is going to have to be in Kelvin. And the temperature of the gas. So the pressure times the volume equals the number of moles times R times T. In a sealed container, we're going to look at a certain case. So a lot of times in these problems, we'll consider a sealed container where the number of moles is not going to change. So we're going to consider gases that go through a change. So they have initial values, which we'll call state 1, and final values, which we'll call state 2. This is the variables to describe the gas when it's in its first state. Then it goes through a transition, and it goes to the second state. In the second state, these variables describe it. Well, if it's in a sealed container, then N1 equals N2. So we can find further relationships between these two. The way we're going to do it is we're going to get N1 by itself. So we divide by RT1. And over here we get N2 by itself. And since N2 is equal to N1, we can set these two equal to each other. Now, on both sides, we have an R value, so that can cancel out. And we are left with, this is the equation that shows what happens to an ideal gas when it's in a sealed container. The relationship between the initial pressure, the initial volume, and the initial temperature, and the final pressure, the final volume, and the final temperature. Now, a lot of times when we look at these problems, we're going to be using a graph called a PV diagram. A PV diagram is a graph showing the pressure on the y-axis versus the volume on the x-axis. It doesn't matter how which variable we're changing first and which is dependent, which is independent. We always do our PV diagrams this way, and that way we can make generalizations about the trends of the PV diagrams. Each point on a PV diagram is a unique state of the gas. We assume the number of moles, N, is constant on a PV diagram, so any problem that uses a PV diagram is going to be in a sealed container. A trajectory is a transition between points on a PV diagram, and from point 1 to point. Sorry, that was a mistake. This should have been point 2. From point 1 to point 3, this is the trajectory that the system took to get there. So let's consider some special cases of trajectories on a PV diagram. Let's say we have a container in state 1 at pressure 1. We're going to keep it closed so the volume doesn't change, but we're going to add heat to it. So the result is that the pressure increases. What it would look like here is the volume is constant and it goes from pressure 1 to pressure 2. This is an example of an isochoric process. An isochoric process is defined as a process where there is a constant volume, and you need to learn the term isochoric. Now let's consider a piston. This piston is at equilibrium with the environment, so the pressure on the inside equals the atmospheric pressure. It has a frictionless piston so that the volume can change without losing any energy. We heat it up, and it has to reach equilibrium with the atmosphere again, so the volume is going to increase, but the pressure on the inside is going to stay the same. This is what it would look like on the graph. We start at pressure 1 and volume 1. And we heat it up so it moves to volume 2, but it stays at pressure 1. This is an example of an isobaric process. An isobaric process is one where the pressure stays constant. And you can remember the term isobaric because bar has the same root as in barometer, which measures pressure also. So an isobaric process is a process with a constant pressure. Last example, we're going to consider a system that is in a fluid that will keep the temperature constant. So this fluid around the piston will keep the temperature constant. The volume is going to change. So we have one system, and then we're going to apply pressure to it. When we apply pressure, we end up with a new pressure and a new volume. So both pressure and volume are going to change, but the temperature is going to stay constant. So we have our initial value with the larger volume and the lower pressure. And this we will call the initial. So our initial volume is going to be the larger volume, and our initial pressure will be the lower pressure. Our final volume will be a smaller volume here, and our final pressure will be greater. So this is our initial, and this is our final. And this is what a PV diagram will look like for this type of process. This is an isothermal process. An isothermal process is one where the temperature stays constant. But because P and V have inverse relationships, they're inversely proportional to each other, the graph of an isothermal process is going to be a hyperbola. So the graph of isothermal process is not a straight line like the other graphs. Now we could also have different isothermal processes on here. And when you have several isothermal processes, they're called isotherms. So depending on the temperature. These isotherms, this might be a 600 Kelvin isotherm, so that has that temperature. This has a 400 Kelvin isotherm. This is a 200 Kelvin isotherm. As you lower the temperature, your isotherm gets closer to 0.